STA 2322 Data Analysis using Statistical Packages. Lesson 4 Data Analysis. Learning Outcomes. Define the terms data analysis, parametric and non-parametric tests, hypothesis testing, null hypothesis and alternative hypothesis, degrees of freedom, normality of data, data transformation. Test the normality of data and data transformation using as SPSS. These are the learning outcomes of this lesson. First of all, we will consider what is the statistical data analysis. This term refers to a wide range of techniques to describe, explore, understand, prove and predict the data based on the sample data sets collect from the population using sampling strategy. So in here you can see there are two words, sample and population and sampling strategies. So you learn these things, I think, in the first semester in the course Introduction to Statistics. You know that what is population, what is sample and what are the sampling techniques. So I am briefly explain those things, not very descriptively, briefly, to just to remind you what you learned. So what is sample and what is population described in statistics? Population. A population is the group of all items of interest to a statistics practitioner. Frequently very large, sometimes infinite. So example is given, population number in country. So if we most probably statistics are using for the researchers. So if you need to do a research, we can't take the entire population, because one thing is, if we are taking the entire population, we need more time and more money to conduct the researches. The other thing is, when we are getting the population and also if we are getting a sample, we take the same results. So if it is not necessary to get the entire population as a sample, because there are no meaning of this, because if you use the correct sample techniques to select the sample, then that will give the same answer as the entire population. So population is the large group, sample is the subset of the population selected for the study is some prescribed manner. So sampling, there are some sampling techniques. So according to those sampling techniques, we have to select the sample from the population. So if we select the correct, if we are selecting the sample from the correct sampling techniques, then sample is the representative of the population. That is not very large. So we can do our research for that sample. Then that will give the as the result same as when we are conducting that research from the population. Right? I think now you have the understand what is the sample and what is the population. Sample is the a subset of the population which are representative of the population. So here you can see that potentially very large but always less than the population. Then if you take this as the population, sample is like this way. But yeah, can you see that there are if you take the circles, there are 4 colors. Then in the subset also the 4 colors, right? It means there is a representative of the population, but population is very large than the sample. Next, data. Information we collect about a topic or subject under investigation. The information collected about the variable may be the singular plural value. So data means the things which we are collecting in research we called as the data. There are the types of data. Data can be several types. Quantitative, basically 2 types. Quantitative, it means numerical data, and the qualitative data. Qualitative data means they're not numerical data, right? Quantitative or numerical data measured of or identified on a numerical scale. It means numbers. Quantitative data we can represent by numbers, can be analyzed using statistical methods, and results can be displayed using tables, charts, histograms and graphs. So the quantitative data we can analyze using the statistical method, and results can be interpreted by the using table, charts, histogram, graphs and the other methods. So may be further classified into two distinct groups. So then quantitative and qualitative data we can classify further for the interval data and the ratio data. Quantitative interval data, so it is ranked. Interval data is ranked, measure a precise difference between units of measurements, defines value in which defines value in such a way that the interval between two values is meaningful. Then quantitative ratio data, the data possesses the characteristics of the interval measure except that meaningful zero exists. So in here that there are in the qualitative interval data, in the quantitative ratio data, then there is no meaningful zeros exist. True ratio exists when the same information is collected from two or more subjects. The ratio of the data value is meaningful. So quantitative data can be divided into two distinct groups, that is interval data and the ratio data. Then quantitative data involves amounts, measurement, anything of quantity, it means numbers. Example for the quantitative data would be counts, so any number. So it means there are 643 dots on the ceiling, there are 25 pieces of chocolate, there are 8 planets in the solar system. These are the quantitative data. Measurements, the measurement also the quantitative data. The length of this table is 1.892 meters. The temperature at 12 p.m. was 18.9 degrees Celsius. The average flow yesterday in this river was 25 miles per hour. Then qualitative statistical data. So qualitative data means non-numerical data, but there are some statistical data in the qualitative. There are some statistical data can be found from the qualitative data. So the qualitative statistical data is the data which is expressed in words rather than numbers. It means if you select something, if you are observing the colors are not the numbers, right? Colors can't be represented in the numbers, right? It can be if we are taken converted in the numerical values, but if we taken as it is, that is we can't represent in numbers. Those are qualitative data. These are measurements that cannot expressed on numerical scale. Examples: hair color, so we can't express in numerical scale. Province you born, astral sign, then area codes, gender, male, female, of each of the 125 applicants of the managerial position in a firm. Qualitative data can be further divided into here's qualitative data we can divide into two, that is numerical and non-numerical data. Then again we can divide into ordinal and nominal. Yes, you know that there are 4 scales. Now earlier we talked about 2, that is ratio and interval. Here there are another 2, nominal and ordinal, altogether 4, right? Qualitative nominal data. The data consists of the number of participants falling in various categories. Example, fat, thin, male, female, like those things, the qualitative nominal data. Qualitative ordinal data, classified into the categories that can be ranked. So if we are taking this order, this can be ranked. No, they provide information about the relative comparison, has no precise difference between the ranks, may be either numeric or non-numeric. Qualitative ordinal data can be numeric or non-numeric. It means if we take the 5-point scale, 5-point scale means agree, then strongly agree, then agree, then neither agree or disagree, then disagree and strongly disagree. There are 5, no? So we can mark 1, 2, 3, 4, 5. So if we mark like this way, that's come as numbers, no? Then we can take those numbers as the quantitative variables, and we can do this. We can use the statistical methods to analyze data. So qualitative ordinal data, that they can rank. Then one example is uh, 5-point scale. There are some more scales: 2-point scales, 5-point scale, 3-point scale, 7-point scale, 4-point scale, 6-point scales. So those are the examples for the qualitative ordinal data. Key steps in statistical data analysis: state your research objectives. You know that as I explained earlier, we used statistical data analysis method for the researchers. So when we are doing the researchers, we have the research objectives. So first we have to start the research with research objectives. So that is the first thing. Then decide which variable or variables in your data set questionnaire can be analyzed to answer the research objective. So then questionnaire, so data set. So there are some words, these things are used in when we are doing the researches. So then questionnaire means one of the data collection methods. So you know that there are several methods to collect the data from the others, so we can do the observations. That is one thing. Observation, then interviews. There are some types of interviews called structured interviews, semi-structured interviews, then unstructured interviews, or we can do the participant observation, or we can use the questionnaire, or there are several methods so we can use. Then here questionnaire means one of the data collection methods. So we have to decide which variable in our data set, and how we can analyze the research objectives. Then third step is decide what statistical analysis technique is suitable. This depends on the number of factors. So we have to define the which statistical technique is suitable. So we are going to talk about the statistical techniques in the next lessons. So then after we learn those things, you can decide which is best method to analyze this data based on the number of factors. Then whether the analysis will involve, if it is one variables, that means univariate analysis. If there are two variables, that is bivariate analysis. So more than two variables, we told that is multivariate analysis. Then there are two types of test. One is the parametric test, the other one is the non-parametric test. So in this lesson we are going to talk about the parametric test, and you can learn about the non-parametric test in the next semester. There is a separate course called non-parametric tests. So you can learn those things in that course. Then here we are going to consider about the parametric test. So when we use them, and which is more powerful. So parametric assumptions, when we need to do the parametric test, we have to do those assumptions. Following assumptions should be made before performing the parametric test. The observations must be independent. The observation must be drawn from the normally distributed populations. These populations must have same variances. So you know that so what is normal distribution? No, I think you learn those things in the introduction to statistics. Yes, in the first semester. So then when we are taking the observation, so it should be in the normal distribution, otherwise these parametric tests are not valid. So normal distribution means, you know, that bell-shaped one. So then the populations of the population must be have the same variances. If we are taking the normal distribution, it has the same variances. So these are the examples, some of the examples for the parametric tests: t-test, regression, correlation, ANOVA, then z-test. There are some more. Then non-parametric assumptions. Observations are independent. Variable under study has underlying continuity. Examples for the non-parametric test are given, that is Wilcoxon's signed rank test, and this one is called Wilcoxon rank sum test or Mann-Whitney U test, and Kruskal-Wallis test, Friedman test. So you can learn these tests about these tests in the non-parametric test course. And I think you already know about the hypothesis testing. These things are covered under the statistical inferences. So I will briefly explain what is hypothesis testing based on our lesson. I am not going to deeply discuss what is that. So hypothesis testing means when we are doing the quantitative research. So this data analysis is based on the researchers. When we are doing the quantitative research, we have to state the hypothesis. It means we are predicting based on the previous experiences we based, that's this can be happen, right? Based on those hypotheses we are going to do the research and analyze data, and we are going to prove this hypothesis correct or wrong. So that's then hypothesis testing. Statisticians follow a formal process to determine whether to reject a null hypothesis based on sample data. So there are two types of hypotheses. First one is the null hypothesis, the other one is alternative hypothesis. I will explain in briefly what is null hypothesis and alternative hypothesis, right? This process called hypothesis testing consists of the 4 steps. The hypothesis testing consists of 4 steps. First one is state the hypothesis. This involves the stating the null and alternative hypothesis. So first we have to state the null and alternative hypothesis. The hypotheses are stated in such a way that they are mutually exclusive. Sure, we have to state this hypothesis such a way that mutually exclusive. I think you know about what is mutually exclusive. When we are thinking about the sets, mutually exclusive means there are no intersection between two sets, so then it is mutually exclusive. It means if we state the hypothesis, suppose a null hypothesis we can represent as this way: there is no significant difference between two groups. No significance difference, that is the null hypothesis. If it is no significant difference, we can have to state the alternative hypothesis as there is a significant difference, right? Null hypothesis, there is no significance difference, but alternative hypothesis, there is a significant difference, right? So that's why here stated as that hypotheses are mutually exclusive. That is what if one is true, the other must be false. Yes, that will happen in the experiments. If we say there is a significant difference and the other one says there is no significant difference, if one is false, the other one must be true, right? So that is the nature of the null hypothesis and alternative hypothesis. Then the second step is formulate an analysis plan. The analysis plan describes how to use the simple data to evaluate the null hypothesis. So this is how we are going to do the analysis plan, right? Analyze sample data, find the value on the test statistics, mean, then mean, proportion, t-score, z-score, etc., described in the analysis plan. So next thing is this one. Then finally we have to interpret the results. After getting those results, we have to interpret it, apply the decision rule describes in the analysis plan. So these things we have to do when we are doing the hypothesis testing. If the value of the test statistics is unlikely based on null hypothesis, reject the null hypothesis. There are some criterions. So when we how to reject and how to accept the null hypothesis, we will discuss in the same lesson later how we can accept and reject the null hypothesis. So then based on some values we are going to reject and accept the null hypothesis. Then setting up a testing hypothesis is essential part of the statistical inference. That is essential part of the statistical inference. In order to formulate such a test, usually some theory has been put forward, either because it is believed to be true or because it is to be used a basis for argument, but has not been proved. So then normally hypotheses are based on some theories, but it is not proved. So based on the research we are going to prove, or we are going to tell that is not true. For example, claiming that the new drug is better than the current drug for treatment of some symptoms. Here take that thing into your mind. Based on this we are going to state the null and alternative hypothesis, right? Claiming that a new drug is better than current drug for treatment of some symptoms. Then here they consider about two drugs for some disease, some symptoms. So a researcher needs to examine whether new drug is better than the current one, right? That is the thing we need, right? That is our research. So based on this one, we have to state the null hypothesis and alternative hypothesis, right? So what is our research? Claiming that new drug is better than the current drug, right? Now we will consider how to write the null hypothesis and how to write the alternative hypothesis. In each problem considered, the question of the interest is simplified into two completing claims, hypotheses between which we have a choice. The null hypothesis denoted by H naught, right? So null hypothesis, normally we denote that H naught, against the alternative or experimental hypothesis denoted as H1 or HA. The both notation we can use H1 or HA for the alternative hypothesis. Then null hypothesis. The null hypothesis H naught is usually the hypothesis that some observation results purely from chance. It represents a theory that has been put forward because it is believed to be true or because it is to be used as basis for the argument but has not been proved. So I explained that earlier. For example, in clinical trial of a new drug, the null hypothesis might be the new drug is no better than on average than current drug. So this is our case. So what we are going to do is, then we need to test this one, claiming that new drug is better than. So first thing is, in the null hypothesis we are going to tell no, it is not better than, right? So we need to test is that it is better than or not, right? But we are stating the null hypothesis as this way: the new drug is not better than the current drug, right? That is the null hypothesis. We are taking null means we are taking the negative part. The new drug is not better than the current drug. That is the null hypothesis. I think same thing is explained there. Yes, that is not, for example, new, it means not better than means there are no difference between two drugs on average. So so we can write the null hypothesis as this way: there is no significance, that word should be there. There is no significance difference between the two drugs on average, right? We need to check whether the new drug is better than the old drug. But so we are stating this, the null hypothesis, as there is no significant difference. Keep that phrase in your mind, because each and every time you have to start as like this: there is no significant difference. In when we are stating the null hypothesis, then you have to take the other part from according to the problem. There is no significant difference according to this problem between the drugs on average, the two drugs on average. I think you can understand what I am going to say. So according to the problem, we have to write the null and alternative hypothesis. Then it is started from there is no significant difference between. Here we need to text the new drug is better than the old drug. So we are writing there is no significant difference between the two drugs on average. That is the way of we are writing the null hypothesis. We give the special consideration to the null hypothesis. This is due to the fact that the null hypothesis relate to the statement being tested. So we are going to test these null hypothesis. Is there a difference? So we state that there is no difference. So then we have to check is there a difference, right? So whereas the alternative hypothesis relate the statement to be accepted if when the null is rejected, right? So then we are going to test there is a difference. We wrote that there is no significant difference. So that is null hypothesis. But if it is not correct, so there may be alternative. That's why we are writing the alternative hypothesis next. Now we wrote the null hypothesis: there is no significant difference between two drugs on average. That is our null hypothesis. But if sometimes it after testing the hypothesis by using the statistical method, it can be wrong, and it should be rejected. So that in that case we have to write a alternative hypothesis. The final conclusion, once that has been carried out, always given in terms of the null hypothesis, right? Final conclusion. So final conclusions: reject null hypothesis in favor of alternative hypothesis, or do not reject null hypothesis. So these things, rejecting and accepting null hypothesis based on some statistical techniques called some values. So we will discuss that in later. Now keep into your mind. So you have to reject or accept the null hypothesis based on the statistical results which we are gained from our statistical test. Never conclude, reject alternative hypothesis, or often accept alternative hypothesis. We are not like that way. We are rejecting alternative hypothesis, we are not writing, we are testing the null hypothesis. If it is rejected, we are writing we reject the null hypothesis in favor of alternative hypothesis, right? So we are not writing without writing rejecting null hypothesis, we can't write directly we are accepting the alternative hypothesis. That is wrong way of writing the conclusions, right? Rejecting the null hypothesis then suggests that the alternative hypothesis may be true. It may be true, right? There is some probability, right? It is not directly said that is true, it may be true, right? But we test the null hypothesis, we know that if it is not correct, it is definitely not correct. If it is correct, definitely correct. But we can't say that alternative hypothesis 100% that's correct. We telling that it may be true, right? There is a probability it may be true or not. Then when we consider about the alternative hypothesis, the alternative hypothesis we are normally denoted at H1 is a statement of that what statistical hypothesis is test is set up to establish. It is hypothesis that sample observations are influenced by some non-random cause. For example, in a clinical trial of a new drug, the alternative hypothesis might be the new drug has different effect on average compared to the current drug. So what we need to test in the previous example, the new drug has a more better performance than the old drug. But we take the null hypothesis as there is no significant difference between two drugs on average. So then what is the alternative hypothesis? As explained in earlier, there is a no significant difference, right? So the two drugs have different effects on the average, right? The alternative hypothesis might also be a new drug is better on average the current drug. So we can write the alternative hypothesis that the new drug is better than the current drug on average, or we can write as same as the alternative null hypothesis, that is easier than this way, right? So we take there is no significant difference between two drugs. Then what we can write as alternative hypothesis, that is easier than this one. There is a significant difference between two drugs, right? There is a significant difference between two drugs. Okay, so we can't tell that it is better than current drug or not, because we test the null hypothesis, no? So null hypothesis we taken as there is no significant difference between two drugs on average. So then we can write the alternative hypothesis other than this one. This is also correct, but better thing is we can write there is a significant difference between two drugs on average. So that is enough, right? I think now you have idea how to write the null hypothesis and alternative hypothesis based on a statistical test. So some more examples on null hypothesis and alternative hypothesis. Suppose we wanted to determine whether a coin was a fair and balanced. A null hypothesis might be that half the flips would result head and half in tails. The alternative hypothesis must be the number of heads and tails would be very different. Symbolically, this hypothesis would be H0 we can write this way, and HA we can write this way. That is in symbolically. Otherwise you can write the in words. How we can write what we have to deal whether a coin was fair and balanced. So we can write null hypothesis, half null hypothesis might be half the flips would result in heads and half in tails, right? This is the null hypothesis. It means we can write null hypothesis there. We can take the half the null hypothesis, half heads and half tails. this is the null hypothesis, and the other one is then we take the for the other side, that is alternative hypothesis. Suppose we flipped coin 50 times, resulting in 40 heads and 10 tails. Given the results, we would be reject the null hypothesis, right? If that our test is, if after completing our test we take the results as this way, so if it is not correct, what we have to do, we have to reject our null hypothesis in favor of the alternative hypothesis, right? If we reject those null hypothesis, then we remaining the alternative hypothesis, and we can accept that as true. We would conclude based on the evidence that what the coin was probably not fair and balanced. Okay, according to this test, the coin was not probably, again it is not told directly, it was not probably not fair and balanced. So that is all, that is about the null and alternative hypothesis. That is the most important part in this lesson, because when we are doing the analysis part, very first thing is we have to state the null hypothesis and alternative hypothesis. If you do not state that correctly, what happened, your whole interpretation part is wrong, right? So that is the very basic thing, and that is very important thing. You have to understand how to write the null hypothesis and alternative hypothesis. Based on this, you have to do the interpretation part of the problems. The null hypothesis and alternative hypothesis can be chosen according to the given problem, right? Now I explained two examples how to choose the null hypothesis and alternative hypothesis. Then next thing is degrees of freedom. The terms of the degrees of freedom, that is not degree of freedom, that is degrees of freedom. The term degrees of freedom indicates how much freedom or independence there is within a group numbers. For example, if you want to sum 5 numbers to get the total, we have the freedom to select any number you like. However, if the sum of 5 numbers is stipulated to be 92, so we take a number, then sum should be 92, right? If we take sum equal to 92, then choice of 4 numbers, the choice of 4 numbers is fairly free, but the last choice is restricted from the condition of sum must be equal to 2. It means we have to select, according to this example, we are going to select 5 numbers, then sum should be equal to 92. Then we can select any 4 numbers as we like, less than to get the 92 as the sum as our wish, only for the first 4 numbers. Here that is the example described further, so I will explain this. For example, if your first 4 numbers chosen at random are 20, 18, 12 and 32, these numbers added up to 82. If you added these 4 numbers, you get the answer as 82. We get these freely, right? We have any freedom to take these 4 answers. Then but there is a condition. What is it? Sum should be equal to 92. Then we select 4 numbers, then that is sum 82. But fifth number we can't chosen according to the our wish, because the sum should be 92. Then it is naturally come the what is the fifth number, that should be 10, no another number, that should be 10, right? So then the last number is no freedom to choice, right? We can, if we need to select 5 numbers, we can select only 4 numbers as free, right? So then 10 must be selected to make the sum come out to 92. You cannot select any other value. Therefore the degrees of freedom have been limited to by 1, and only n minus 1 degrees of freedom remain. So it means if we have if we are doing a test with n trials, right, what is our degrees of freedom? One does not have freedom. It means our degrees of freedom is n minus 1, right? If the number of trials are n, then degrees of freedom is equals to the n minus 1. In a scatter plot, when there is only one data point, you cannot do any estimation of the regression line. So if you have only one thing, we cannot do. So we know that if we need to draw a graph of a line, at least we need at least two we need to draw that graph. The line can go any direction as shown in the following graph, this graph. Then you have no degrees of freedom here, no degrees of freedom, because n minus 1 is equal to n is, if n equals to 1, then n minus 1 equal to 0. In order to plot the regression, you must have the at least 2 data points. I explained, no, at least 2 data points we need to indicate the following scatter diagram. In this case, you have 1 degrees of freedom for the estimation, that is n minus 1 is equal to 1 where n equals to 2. In other words, the degrees of freedom tells you number of useful data for estimation. So it means so n minus 1 gives degrees of freedom means number of useful data for our estimation, right? However, when you have 2 data points only, you can always join them, be a straight regression line, get the perfect correlation 1.0. So if you have only 2 points, nothing to do, we are just make the straight lines, and then you know that correlation, then if it is like this way, then correlation equals to this side. If you take, what happen, correlation equals to +1. Thus the lower degrees of freedom is poor the estimation is. So if we have a lower degrees of freedom, that is poor estimation. Decision rules. Now we come how to decide our null hypothesis is true or wrong. The analysis plan includes the decision rules for the rejecting the null hypothesis. In practice, statisticians describe these decision rules in 2 ways: with reference to a p-value or with reference to a region of acceptance. There are 2 ways we discuss those things with reference of p-values. So we doing both ways. With reference to the p-value, we can take the p-value by using the SPSS, and also the regions acceptance we can do this is in manually also. P-value also we can calculate manually, but that is a long process, that is a complex calculation. But when we are doing the reference with the region acceptance, we can do calculation manually a little bit easily, not like when we are doing the operations using the SPSS. But if we are referring the regions, we can do the calculation manually also. We will consider how to do the manual calculations. Then hypothesize p-value. So then p-value, here p-value we can taken from the SPSS. Hypothesis p-value. P-value shows the probability your sample test statistics support the null hypothesis as true. So that is the probability. P-value means the probability to be true our null hypothesis. The smaller p-value, the less support the null hypothesis, and the higher probability support the alternative hypothesis. Less value support to the null hypothesis, and greater p-value support to the alternative hypothesis. For example, if we take the p-value as 0.55, indicates the high support for the null hypothesis, you cannot reject the null. So to reject the null hypothesis, there is a significance level, right? So there is a word significance level that is given in the questions. Sometimes they are given 99% significance level, sometimes most probably given 95% significance level. It means 95 means if we divide by 100, that is 95% means 95 over 100, no, that is 0.95, right? That is the probability. If you subtracted that from 1, right? So we know that 95% means 95 divided by 100, no, that is 0.95. If we subtracted 0.95 from 1, what happened? The answer is 0.05. So in that case, if we have 95% significance level, then the value is less than 0.05. So what you have to do, you can reject the null hypothesis. Here value is 0.55. 0.5 means, okay, I told that 0.05, it is greater than 0.05. So that is high support to the null hypothesis. Then we cannot reject the null hypothesis then, right? P-value is greater than 0.05. That's 0.05 coming to according to our significance level, right? That is given in the questions. So here in that case we can't reject the null hypothesis. A p-value of 0.001 indicates the low probability, that is less than 0.05. also less than 0.01 also, no, then less low probability of the null hypothesis is true, so support the rejecting the null hypothesis. If p-value is less than 0.05, so we can reject the null hypothesis. The practical approach is to calculate the p-value and compare with the level of significance. I told you, no, see, level of significance, it is given in the question. If it is 95, then level of significance alpha value is we are taken as 0.05. If it is 99 means 99 means 0.99. If you subtract it from 9, that is alpha is become as 0.01, right? If the p-value is smaller than alpha, we can reject the null hypothesis. Keep this in your mind. So this is very important sentence. If the p-value is less than alpha, we can reject the null hypothesis. So based on the p-value, that is the decision rule. P-value less than alpha, alpha means the significance level that is given in your question. So if it is 0.05, so you get the p-value. If you analyze this using the SPSS, you got the p-value as some value, but if it is less than 0.05, what happens? You can reject the null hypothesis, right? For example, p-value is 0.001. So then now our test given that 0.05, then alpha is set to 0.05. Then what happened? 0.001 is less than 0.05. That is a very small value if we consider this one. Then what happened? So we can reject the null hypothesis. You have a strong evidence to reject the null hypothesis because p-value is much smaller than alpha, right? That is the decision rule. You have to keep this in your mind. If p-value is less than alpha, it means alpha means the significance level, right? It is normally 0.005. That is not always 0.05. Normally it is 0.05. It is given in equation. If it is 99%, then alpha is become 0.01. If it is 95% significance level, that is alpha is equal to 0.05. So if our p-value is less than for the significance level, it means the alpha, p less than the alpha, what we can do, we can reject the null hypothesis. That is the decision rule. Keep that in your mind. So here that is given. The smaller p-values relation to the alpha more than evidence to reject the null hypothesis. So here look at this one, p-value less than alpha. What you can do? If p-value is less than alpha, we can reject the null hypothesis. If p-value is greater than alpha, what we can do? Do not reject the null hypothesis. These are the decision rules. So you have to keep these things in your mind, because when you are doing the interpretation, you need this. Based on these p-values, you have to write your conclusions, right? So the very important part. So some of you thinking about if you can do the analysis using the statistical packages. We can enter the data into statistical packages when you can use the commands and take the answers. But no, that is not carries the more marks, because if we enter the data for the SPSS and if you use the correct command, what happen? It is automatically gives those values, but no need of skills, no need of knowledge of knowledge of the subject matters to do those things, right? That is mechanically you can do, but more marks carries in your examination for the interpretation parts. So you have to interpret your findings clearly. So for that things you need those decision rules. So keep it in your mind. If p-value is greater than alpha, alpha means the significance level, it is given in the question, you can't reject the null hypothesis. But p-value is less than alpha, what you have to do? You have to reject the null hypothesis and accept the alternative hypothesis. Yeah, p-value is greater than 0.01, sorry, greater than 0.1. what happened? No statistically significant evidence for rejecting the null hypothesis, right? If p-value is in between 0.1 and 0.05, weak evidence of rejecting null hypothesis. But if it is less than 0, weak evidence of rejecting null hypothesis, right? P-value is in between p-value less than 0.01 but greater than 0.01, but strong evidence of rejecting the null hypothesis. If it is less than 0.01, overwhelming the evidence of reject null hypothesis. So that is like same way. So this is the way of you are doing rejecting and accepting null hypothesis. Checking for normality and normalizing transformations. So you can apply those tests only for the normally distributed data. At the beginning I explained you what are the assumptions need to apply the parametric test. So it should be normally distributed. So if we have the data set, we don't know if it is normally distributed or not. So what we have to do before doing the parametric test, we have to check if that data set is normal or not. Parametric statistical test methods valid only when a sample x1, x2 to xn has come from a population distribution that is least approximately normal. So it should be normally distributed data. You know that normal distributed data normally bell shaped. This is bell curved, right? The normal distribution is pattern of the distribution of the set data which follows the bell shaped curve. So I am not going to explain what about the normal distribution, because you well known about the normal distribution. You discuss those things and how to find the z values. Those things you discussed in previous courses. So this distribution is sometimes called the Gaussian distribution in honor to Carl Friedrich Gauss, a famous mathematician. The bell-shaped curve has several properties. So you know that these things. What are the properties of bell-shaped curve? The curve concentrated in center and decreases either sides. So it is center and decreases either sides. Here mean, median and mode in one line in the normal curve. This means that data has less of a tendency to produce unusually extreme values captured to some other distributions. The bell-shaped curve is symmetric. Here that is symmetric. 50% in this side for the mean and 50% for this side, mean, median and mode. For you can see in the middle. This tells you that the probability of deviations from the mean are comparable in either direction. Many statistical tests or procedures assume that data follows a normal distribution. All the following statistical tests, statistics or methods assume data is normally distributed, right? So normal assumption need to be there when we are doing the statistical test. Hypothesis tests such as t-test, chi-square test, f-test, ANOVA, analysis of variance, least square regressions, those tests we need to be data to be spread out from the normal distribution, otherwise you can't apply those parametric tests. Before applying the statistical method that assumes normality, it is necessary to perform a normality test on data. So first we have to test if the data is normally distributed or not. We hypothesize that our data follows the normal distribution, and only reject this hypothesis if we have strong evidence to the contrary, right? So while judge the normality of the data by simply creating a histogram of data. So that is we can check simply creating a histogram. No, here if we create the histogram, we can see that if it is normally distributed or not. This is not an objective method to test for a normality, but this is not very good method to take the normality, especially with the sample sizes that are not very large. If the sample size is not very large, if that is not very good method. So with the small sample sizes, discerning the shape of the histogram is difficult. So if we have you know that, no, if you are doing the previous courses, you know that we for do the normality assumptions, data at least greater than 30, no, n greater than 30, otherwise you can't do the normality assumptions. If the data set is very small, we can't do the normal assumptions. So and also we can't apply the parametric tests, but there are some conditions we can use some tests to check whether the data are normally distributed or not. Furthermore, the shape of the histogram can change significantly by simply changing the interval width and the histogram bars. right? Normal probability plotting may be used to objectively access the whether data comes from the normal distribution even the small sample sizes. So on a normal probability plot, data shows follows the normal distribution will appear linear. This is the normal distribution. If you draw the normal distribution plot, you can see if it is go like this, this is the normal distributed data. If the data is go like this way, that is not normal distributed data, right? That is a regression line. So you can use data regression. If it is go like this way, that is this is cumulative probability, then this value. If the data is if you plot the normal probability plotting, so if you can see this is in a linear way, it means the data follows a normal distribution. If it is a curve one, it means that is not normal distribution. So now we consider how we can do the normality test by using the SPSS. Okay, so checking the normality of the distribution with SPSS. There are several ways in which you can use the SPSS to assess the normality of a distribution. Assessing normality is by producing a histogram. First thing is you can assessing by producing a histogram. Assessing the normality of the distribution by producing normal probability plot, PP or QQ plot. So these plots, no, you can draw these plots. First one is producing histogram, second one is producing PP or QQ plot. For a normal distribution, the probability plot should show the linear relationship. I explained, no, if it is normal distribution, the relationship is linear, right? The one is the histogram, other one is PP or QQ plot. The third one is Kolmogorov-Smirnov test. If the sample size is greater than 50, or the Shapiro-Wilk test, the sample size is smaller than 50. So there are two tests. So you can use the Kolmogorov-Smirnov test. The sample size should be greater than 50, right? Otherwise you have to do the Shapiro-Wilk test if the sample size is smaller than 50. Don't worry about these tests. These are inbuilt tests in the SPSS. You have to use only the commands, right? So you have to know about these tests because there are some criteria to test whether that is normal distributed or not, that is given in here. So what you have to check the table, that is significance value. So if you do these tests, there is a table that you can find a significance value from that table. The convention that significance value greater than 0.05 indicates the normality of the distribution. So if once you once you do the Kolmogorov-Smirnov test or Shapiro-Wilk test, it produces the p significance value. If that value is greater than 0.05, then it indicates the normality of the distribution, right? If the significance value greater than 0.05, you can say that your data set is normally distributed. So there are three ways. One thing is the histogram, the other one is PP and QQ plot, the other one is Kolmogorov-Smirnov test, or that is for the sample size which is greater than 50, or if it is less than 50, you can use the Shapiro-Wilk test. Now we will consider how do you check the data for the normality using SPSS. So open the SPSS data file and data in new file. Analyze descriptive statistics, explore. Select one or more dependent variables. So you can use one or more dependent variables, right? I explained you can do the analysis. You can check normality by using one dependent variable or multiple variable at once. Click statistic for estimated, outliers, percentiles and frequency tables, right? You have to select those options. Click plots the histograms, normal probability plot and test, and the spread versus level plots with the Levin statistics, right? First we can do this part. There are some data sets. There are 4 different data sets, right? I'm going to what are the steps? Analyze descriptive statistics, then analyze descriptive statistics, then explore. Explore is you can see in here. This is the part, no? Analyze descriptive statistics, then explore. We have to click here. I already select the data set. Then what we have to do next? We went to this. Now we can see this dialog box. No, yeah. Then we have to select the dependent variable. So I am selecting data set 1. If you need, you can select the data set 3 or 4 at once. No, doesn't matter. Here I select only 1. Then what we have to do, click the statistics. Then this one, statistics, we can click here. Then we can get estimators, outliers, percentiles, frequency tables. So here and estimators, outliers, we can enter. Then confidence level, it is given here, right? So if it is 95%, we have to put in there. Normally by default it is 95%. Sometimes in the question it is given that is 99%. If that case, what you have to do, you have to change this 95% into the 99. Continue. Then what else? Click plot for histograms. Here, plots. Then you can use the histogram here. You can see, you can click on the histograms. So if defaultly this is clicking, if you need no need of the box plots, you can click the none. Then histogram, and also here you can see here normality plots with test. So you have to click on there. Then it gives the normality test with plots. Then click continue. Right. So then we can go to the statistic box. Then descriptives, M outliers and outliers, M estimators and outliers. What is the other one is we can go to the options. Sorry, plots. No. Here statistic we can click descriptive, M estimators and outliers. Right. Click continue. Explore plots dialog box display the normal probability and detrended normal probability plots, the Kolmogorov-Smirnov statistic, and the Lilliefors significance level for texting normality is displayed. Right. Histogram with normal curve. After you okay, you can now earlier we use only the data data entering viewer. No, so we are not using the output viewer. Up to now we have to use the output viewer. So if you are doing something in the output viewer, what you have to do is you have to select separately data set separately and output separately, right? So then you can here see the histogram with normal curve, the box of results, Kolmogorov-Smirnov. Here you can see the Kolmogorov-Smirnov and Shapiro-Wilk test. So then in that case, if sample size is greater than if it is greater than 50, we can use the Kolmogorov-Smirnov test. The significance value is given there. So here significance value is given there. So you can take the significance value from here 0.1 is greater than 0.05. It means what happened, this data is normally distributed. If our n is 10, no, here n is 10, here this you can see, it means you can't use a Kolmogorov-Smirnov test. But why? Because n is greater than 50 only you can use a Kolmogorov-Smirnov test. Now what we have to take the Shapiro-Wilk test. Then we'll check that is 0.318. So it is more greater than 0.05. It means that is normal. So if you look at the histogram, you can say that is normally distributed. No. Right. So now we can see this. Continue. Then we have to press OK. Then what happened? You can see that is in our output window. Right. So there are some here. M estimators given, extreme values. Here that is test for the normality. So if you can see there, our data n equals 20. N equals 20 means again that is not equals to that is less than 0.05. Then less than 50 means we can't use the Kolmogorov-Smirnov test. So what we have to do is we have to use the Shapiro-Wilk test. If we consider the value that is 0.311, 0.311 means that is greater than 0.05. It means the data is normally distributed. You can see the histogram, but there are no curve, no. So here the text normally QQ plot, that is linear. Yeah? If QQ plot is linear, and dependent one, that is also linear. If that is linear, what you can see, that is a normally distributed one. Yeah. So if you need histogram with the normal plot, what you have to do, go for the analysis, right, descriptive statistics, then frequencies, right. Then there is a, you have to select the variable. There is a option called charts. Yes, go to the histograms, hit here, and with normal curve, right. What is our steps? Analyze, descriptive statistics, frequencies, then charts, histogram with the normal curve. Continue. Okay, right. Now you can see this one, no, with the curve. You can see this is normally distributed, right. The three ways I explain, no. First one is the normal curve. Yes, that is normal curve. You can see that is normal distributed. Second one is the QQ plot here, that is linear, it means normally distributed. The other one is these two tests for the normality. Here in that case we can't use a Kolmogorov-Simoneau test because the data set is less than 50. Then we have to use a Shapiro-Wilk test, that is significance value, that is given as 0.3. 0.3 means greater than 0.05. It means that is normally distributed, right. So I am considering another data set. I think we will check the data set 3, analysis, descriptive statistics, explore. I am taking this for this side and taking data set 3 and do the same thing. Statistics, yes, plots, same plots, options, okay, then okay. Now we'll see what happened. Explore. Now we consider estimated, no, yeah, the test for the normality. What is our value? 0.0. It means less than 0.05. It means, what is the meaning? Our data set is not normally distributed. So if it is normally distributed, what happened? This should be greater than 0.05. So then this data set is not normally distributed. We can't apply the test, right? If it is only normally distributed, we can do the test and check whether our null hypothesis is true or false. If it is not normally distributed, we can't use the parametric test, right? So here 0.05. Here we can't see the histogram shape, no. Then we have to take the other one. Then QQ plot, that is not like, no, that is not like a line. It is line is there, so it is in other way. So we can take that histogram, analyze, descriptive statistics, frequencies. We have to take the data set 3, then statistics, sorry, charts, histogram with normal curve, then okay. So we'll see, yes, that's a part of a normal curve, that is not a normal. So this data set 3 is not normally distributed. I think now you understood how to check the normality of data. Another thing, I will explain at last. So when when we are doing the examination, so and the tutorials, the data set, data file, the three things you needed, no. First thing is data set, the other one is the output window, the other one is you have to create a Word document which displays those outcomes and you have to interpret the results, right. So I'll explain at the end of this lesson how to make the that document. So we will go to the next slide. Then data transformation, right. I told you how to transform the data in the previous lesson, but you don't know what is the purpose of the data transformation. So data transformations are the important tool for the proper statistical analysis of the biological data. There are an infinite number of transformation you could use but better to use transformation that commonly used in fields such as there are so many transformations, but normally we are using square root transformation for the count of data. So we take the square root of the given data. Log transformation for the size data. Then an unclear transformation do many people have heard of, and it is important you to which transformation use, because the statistical test you have a large number of observations. Compare this effect different transformations on normality of the variable. If you have small number of observations, you may not be able to see much effect on the transformation on normality, right? If you have a very low number of data set, it means the number of data in the data set is very low. If you are doing the transformation, you can't see very much different, but the data set is very large, you can see the difference. In that case, your decision to use the transformation is based on the convention you feel for the kind of variable. Among many transformation methods, 3 are most commonly used. So there are so many methods most commonly used. We do that, no? Log transformation, you know that how to transform into the logs. Base 10, no? We are using the natural natural logs normally, that is ln. You should specify which log you are using when you are write up the results, as will affect things like the slope and intercept in regression. Many variables in biology have log normal distributions, meaning that after log transformation the values are normally distributed, right? Sometimes that we take that last set, this one, that is not normally distributed, but we can do the transformation. After transformation, sometimes that may be normal, we will check later, right? This because of you take bunch of independent factors and multiply them together, the resulting product is normal, is log normal, right? Log transforms are particularly appropriate if the variance increases with the mean. Square root transformation, the other one is you can take the square root of the given value, that is the square root transformation. This consists of taking the square root of each observation. The back transformation is to the square of the number. You have negative numbers, you can't take the square root, so you know that there is no meaning of the taking the square root of the negative number. So if you have the negative numbers in your data set, you can take the square root transformation. You should add the constant to each number and themselves all positive, but you can do some changes. It means suppose you have minus 20, so you can add any number greater than minus 20, but you have to do for the all data. Suppose you have the data set minus 20, 10 and 3. So what you have to do, if you are adding 50, minus 20 add 50, that is 30. You have to do for the other two also. It means you have 10 plus 50, that is 60, and 3 plus 50, 53. So if you are adding constant, you have to add for the whole data set. The square root transformation is commonly used when the variable is count of something such as bacterial colonies per petri dish, blood cells going through a capillary per minute, mutations per generation, etc. Carrying out the square root transformation will convert data of a Poisson distribution to a normal distribution. So these are some experiments when we are need to use the square root transformation. Then it's carrying the square root transformation will convert the data with the Poisson distribution with the normal distribution. Once it is converted in the normal distribution, we can do the analysis by using those parametric tests. The other one is reciprocal. You know that log transforms does not normalize your data. You could try reciprocal transformation. So what is a reciprocal means? It means you change the numerator and denominator. Suppose you have 5 means normally that is a whole number, but you know that the denominator is equals to 1. 5 divides by 1. So taken reciprocal means 1 over x. It means reciprocal of 5 means 1 over 5. Reciprocal of 10 is 1 over 10, right? Reciprocal of 3 over 4. 3 over 4. What is 4 over 3? Changing up and down, right? So that is the meaning of the reciprocal. This often used with enzyme reaction rate data. And the other one is arc-sine transformation. This consists of taking the arc-sine of the square root of a number. The numbers be arc-sine transform must be range 0 to +1. This commonly used for the proportions which range 0 to 1. So you can do the arc-sine transformation under the compute variable in the SPSS. You can see this. And fifth one is cube. Cube means each data value is cubed, such as taking the square root. You have to take the cube of each and every data sets. Then back transformation. Even though you have done the statistical test on the transform variable such as the log or log of fish abundance, it is not a good idea to report your means standard errors in transformed units, right? After transform, and when you are interpreting results, it is not to use the data in the transformed units. What you have to do, you should back transform your result. This involves to doing opposite of the mathematical functions you used in the data transformation. So it means after doing the statistical test, you have to do the back transformation. It means if you are taking the log transformation, what you have to do, you have to take the anti-log when we are interpreting the results. So if you are taking the reciprocal, what you have to do, you have to take the reciprocal again when you write in the conclusions, right? If we are cubing, if you are take the cube of the data, what you have to do, you have to back transform into the original data by using the cubic root. If you are take the square root approximation, what you have to do, you have to back transform it to the taking the square of the numbers. So that is the way of the interpreting the conclusion. You have to back transformation and take the original data when we are do the interpreting part. You can see there are some untransformed data. When transformed into the square root transformation, 38 becomes 6.164. If you take the log transform, it becomes 1.580, and reciprocal, you can see that it is come as 0.003. You can try this table by using the SPSS and take this transform value. You know that how to transform the data. You have to go for the SPSS. So how to transform the data, you know that. If you are going to SPSS, transform, compute variables, then you can target variable, then you know that how to transform the data, right? So here you can see this is the untransformed data, right? That is not normal here. If you take the QQ plot also, then it is. But if you take the square root transformation, what happen? It is approximately normal. No, that is good than this one. Okay, that's why we are doing this transformation. If the data is not transformed, sorry, it not normal distribution, what you have to do, you have to transfer to another variable and check whether it is normal. Then if it is normal, you can do the analysis part. And when we are interpreting the results, what we have to do, you have to take the back transformation and write the conclusion. And other things here, log transformed one, right? Data transformation using SPSS. You know these things because we discussed in the last lesson also. Anyhow, we will discuss further. For data transformation, two options are available in SPSS: compute command and the transformation method, and explore command dialog box. So explore power transformations. So these are the power transformation: spread values, level tops. To transform data, you must select the power of the transformation. So you know that here how you can explore plots, right? Here you can use the power transformation here. Then you can convert into the natural log, so any value you like. And the other way, you know that, so you have to use data and so transform, compute variables, right? There are two ways to transform data. You can choose one of the following alternatives: natural log, 1 over square root, or reciprocal, square root, square, cube. These are the alternatives you can take. data transformation using a variable command. So that's, you know, that you can use the compute dialog box, computed variables and variables based on numerical transformation other variables. You can perform the following activities using the command: computed variables for the numeric strings variables, create new variables, replace the value of existing variables for the new variables. You know these things because we discussed how to transform compute variables in this previous lesson. No, I'm not going to explain that is again, right? You can read and understand, and you can use the knowledge which we gained from the previous lesson, right? Yeah, this is the way of you can do the transformation, any transformation you will like in this dialog box, right? Okay. Now we will consider how we can do this practically, right? If we take the dataset 3, no, that is not normally distributed, no, so we will see we do some transformation and see whether it is normal, can be converted in normal distribution or not. So we can go to the transform compute variable, target variable with data. We can take log data set 3, right? We are going to take the log of data set 3, that is the target variable. So we can take expression, so arithmetic ln, right? We take the data set 3, then we'll see what happened. Where is it? Yes, log data set 3. Now we have a new variable. Now we will check whether this is normally distributed or not. So we can use 3 types of tests. So first I am taking the now we are going to take log data set 3 and charts. Histogram is normal curve. We will see. Now what happened? Then log data set 3 is normally distributed. So if we transform the data set into the log, it is naturally become as the log data set. So then we will do the other 2 types of test also. Then we can go to the analysis, descriptive statistics, explore, and now we have to take log data set 3 as a dependent variable, then plots. Yes, normality with test and statistics, these statistics. Yes, we can click OK. Then we'll see what happened. Yes, M estimated. Now we need the Shapiro-Wilk test, no, because n equals 20. Now what happened? Earlier I didn't remember, where is it? We'll see. This one, no. Earlier we'll do the Shapiro-Wilk test, what come? 0.00. Now if we transform into the log transform, what happened? Shapiro-Wilk test come to 0.89. 0.89 means that is greater than 0.05. It means that is normal. And so QQ plot here, PP plot and QQ plot, that is you can see a normal line. So that's why we are using this transformator compute variable. So if it is the data is not normally distributed, sometimes it if you take the log values, it cannot be normally distributed. Then what you have to do? You have to take the other type of transformation. You can take the this one, reciprocal, square root, square, or anything you like, right? Okay, then you can convert this into the normal distribution and do your analysis and take the conclusion. Before take the conclusion, what you have to do? You have to back transform the data. If you do something, then what you have to do? Analyze, transform compute variables. Now what you have to do? Take. So when we are doing data set back transformation, next one, right? So we'll see inverse operations, conversion, arithmetic, right? We'll see how we can take the inverse one. Yeah, you know that we take ln. No, ln means inverse is we have to take e to the power. So then we go to the again transform compute variables. Now we delete this one. Now we have to get the inverse one, log, then that is exponential. So ln means then this is the inverse one. So we have to take the log data. Then we will see what happen if you take this. You see log data back. So if that is correct, this is log set data set we take back, so we have to take the original values. Yes, we can take the original values. No, now that is not when that is a simple data set. No, sometimes we are doing the computation, then it is after log transformed, it is not come the original values. Okay, so I think now you clear about these things. So we what we have discussed, we discussed what is data analysis, then parametric and non-parametric test, hypothesis testing, how to write the null hypothesis and alternative hypothesis, what is degrees of data, then normality of the data and data transformation, and how to test the normality of data using the SPSS. I think now you are clear about all of those things, and so based on this lesson also you have a tutorial. So if you have anything to clarify more, you can contact me, right? Okay, then thank you very much.